Welcome to the RBFS Fundamentals training series. MPLS is a pretty deep and broad topic, so we've split it up into two parts. In this first part, we'll walk through the fundamentals of MPLS, covering the data plane and the main signaling protocols. Part 2 will focus on Layer 3 and Layer 2 VPNs. Before we dive into MPLS and how it's implemented in RBFS, just a quick disclaimer. This training clip is provided free of charge for non-commercial use and is intended to help you get up to speed with RBFS on your own. It doesn't cover every single configuration option out there, and some details might change in future versions of RBFS. Here's a quick overview of the topics we'll cover. We'll start with MPLS Fundamentals, explaining the building blocks of MPLS and how the data plane works. Next, we'll take a closer look at LDP, including how it's configured and monitored in RBFS. Then, we'll shift focus to segment routing and explore how it differs from traditional MPLS signaling protocols. After an overview of segment routing, we'll walk through how to configure it using ISAS, OSPF, and BGP extensions. We'll begin by demystifying MPLS, what it is, how it works, and why it's essential for modern networks. From there, we'll explore key terms and concepts that form the foundation of MPLS, which are shared across different implementations. Traditional IP routing protocols like OSPF, ISAS, and BGP distribute reachability information, creating a routing table that maps each IP prefix to a next hop, the next router along the path. When a router receives an IP packet, it looks up the destination address in its routing table to decide the next hop. This process, called longest prefix matching, means the router picks the most specific route that fits the packet's destination. While modern network hardware handles these lookups efficiently, early on, the process was computationally expensive, prompting the development of MPLS. Traditional IP routing also has its limitations. First, each router independently makes forwarding decisions based on its local routing table, known as the hop-by-hop paradigm. This limits centralized control over the end-to-end path, complicating traffic engineering because routers only control the next hop and have no visibility into the entire route. Additionally, new protocols or applications often require extensions to traditional routing protocols. MPLS was introduced to overcome these limitations by reducing the need for detailed header inspection at every router along the path. MPLS stands for Multi-Protocol Label Switching. Multi-protocol refers to the fact that MPLS can work with any network layer protocol, though today it is mostly used with IPv4, IPv6, and IPVPNs. In addition, transport of Ethernet frames across MPLS networks has become quite popular as well. MPLS uses fixed-length labels, which are assigned based on header information like the destination IP address. This labeling process occurs only once, when the packet first enters the MPLS network. When a packet is forwarded to its next hop, the label is attached to the packet. Subsequent hops will use the assigned label as an index to a next hop entry in a forwarding table, rather than inspecting the packet's IP header. This approach has the advantage that intermediate hops do not need full IP routing tables and thus can be implemented on optimized cost-efficient hardware. In addition, these devices don't need to understand the encapsulated protocol at all. Finally, MPLS allows packets to be routed along specific paths, enabling traffic engineering even when those paths are not the shortest. This is a key advantage over traditional IP routing, where routing decisions are typically based only on the most efficient, shortest path routes. MPLS provides a strict separation between control lane and data plane. The control plane refers to the set of protocols that exchange reachability information between routers such as ISIS or BGP. The data plane handles the actual forwarding of packets, based on forwarding tables created by the control plane. In MPLS, this forwarding table is called a label forwarding information base. The MPLS architecture is defined in RFC 3031. According to this standard, a router that supports MPLS is known as a label switching router or LSR. If an LSR operates strictly within the MPLS network and performs only label lookups and switching, it is sometimes referred to as a core LSR, transit LSR, or in MPLS VPNs, a provider router or P-router. An LSR that connects to non-MPLS networks is called an label edge router or LER. In MPLS VPN context, LERs are typically called provider edge routers or PE routers. An LER performs packet classification and assigns labels to incoming packets. It also understands standard network protocols like IPv4 and IPv6 and maintains full IP routing tables. The path from an ingress LER to an egress LER is called a label-switched path. A label-switched path is the path through the MPLS network from an ingress LER to an egress LER. It is important to note that LSPs are unidirectional, so a separate LSP is required for reverse traffic. An LSP does not have to follow the shortest path. This allows for traffic engineering, where paths can be selected based on policy, such as bandwidth or latency requirements, instead of purely routing metrics. In MPLS, packets that are treated identically are grouped into a forwarding equivalence class or FEC. A FEC is mapped to an LSP. All packets belonging to the same FEC follow the same LSP. A FEC might be as simple as a destination IP prefix, or more complex, including source IP, DSCP value, or application-specific fields. An MPLS label is a fixed-length, locally significant identifier that represents a forwarding equivalence class. Ethernet is the most commonly used Layer 2 transport, so this video focuses on Ethernet-based MPLS. In such networks, the MPLS label is inserted as a shim header between the Ethernet and IP headers. This shim header is defined in RFC 3032. The ether type field in the Ethernet header is set to 0x8847, indicating the presence of an MPLS unicast packet. The shim header includes a 20-bit label field. In addition, a 3-bit traffic class field, formerly known as the experimental field, is included, which is used for quality of service similar to Ethernet class of service field or IP precedence. MPLS supports label stacking, allowing packets to carry multiple labels for services such as VPNs and traffic engineering. A 1-bit bottom of stack indicator marks the last label in a label stack. Finally, an 8-bit time to live field is included to prevent routing loops by decrementing at each hop. Note that the MPLS shim header does not indicate the network layer protocol of the encapsulated packet. Label edge routers must infer this information from the FEC to label binding. LSRs examine only the topmost label in a packet stack. In per-platform label space, the label has the same meaning regardless of the interface. This is the most common model used in Ethernet-based MPLS. Upon receiving a labeled packet, the LSR performs a label lookup, which yields two outputs, the next hop router and a label operation. There are three basic label operations in MPLS. The push operation adds one or more labels to the packet. This is typically done at the ingress LER. Pop is the action of remove the top label from the label stack. Label swapping refers to replace the top label with another label. Routers can also combine operations. For example, they may pop one label and push two new ones. We've already discussed that a labeled packet travels from the ingress LER along the LSP to the egress LER. An LSR is considered upstream in relation to another LSR if it is closer to the ingress LER, while the LSR closer to the egress is considered downstream. Thus, a packet is forwarded from an upstream LSR to a downstream LSR. Since MPLS labels are locally significant, different routers often assign different labels to the same FEC. As a result, label swapping is a common operation, replacing the incoming label with the one expected by the downstream router. Labels are always assigned by the downstream LSR and label bindings are advertised from downstream LSR to upstream LSR. The figure illustrates an LSP that spans from the ingress LSR on the left, often called the head end of the LSP, through two transit LSRs, to the egress LSR on the right, also known as the tail end of the LSP. When the ingress LSR receives an IP packet, it first strips off the layer 2 header and performs a lookup. This lookup assigns the packet to an forwarding equivalence class, and consequently, to an LSP. The packet is then tagged with label 67 before being forwarded to the next downstream LSR. Each subsequent router inspects the label and consults its label forwarding information base to determine the next action. The first transit router swaps label 67 for label 44. The second transit router performs a similar swap, replacing label 44 with label 51. Finally, the egress LSR removes the label, and forwards the encapsulated IP packet to a non-MPLS router via standard IP forwarding. In the last slide we've seen that an egress LSR after receiving a packet must first inspect the top label to verify that it is indeed the egress LSR. At this point, the router typically pops the final label to reveal the original IP packet. However, this requires two lookups, one to pop the label, and another to forward the packet using its IP header. To optimize this process, MPLS introduces a concept known as penultimate hop popping. In PHP, the penultimate router, the one upstream to the egress LSR, removes the top label of the label stack. This enables the egress router to directly process the IP packet without extra work. The penultimate LSR is notified by the egress LSR through the implicit no label, which instructs the upstream router to pop the label before forwarding the packet. Now that we've covered the data plane, let's discuss the MPLS control plane. A label distribution protocol is a set of procedures by which one LSR informs another of the label FEC bindings it has established. The MPLS architecture does not define a single label distribution protocol. Instead, protocols focusing solely on label distribution, such as LDP, have been defined. Additionally, existing protocols like BGP, OSPF, and ISIS have been extended to support label distribution. Regardless of the protocol, some core principles remain consistent. Labels are locally significant, meaning only the assigning router knows the meaning of a label. Therefore, labels are always assigned by the downstream router, and the corresponding label FEC binding is advertised to upstream neighbors. There are two models for label distribution. A router advertises label bindings to all neighbors automatically. This is known as downstream unsolicited. On the other hand, a router can advertise only a binding if explicitly requested, known as downstream on demand. When an LSR receives a label binding for a specific FEC from a node that is not its next hop, it has the choice whether to keep such a binding, which is called liberal retention mode, or whether to discard such a binding and only keep labels that are currently in use, or conservative retention mode. Each mode has its advantages and drawbacks. Liberal retention mode allows for quicker adaptation to routing changes, but it consumes more memory to store bindings. Conservative retention mode uses less memory but may slow down adaptation to changes in the network. Finally, there are two modes for label allocation. In independent control, each LSR allocates a label for a FEC and distributes it to its neighboring LSRs, regardless of the labels assigned by other routers in the network. This is similar to the behavior of standard IP routing protocols. With ordered control, an LSR allocates a label to a FEC only if the downstream router has already done so. Now that we've covered some general concepts about the MPLS control plane, let's move on to LDP, the Label Distribution Protocol, which is a widely deployed mechanism for distributing labels in MPLS networks. LDP is a protocol used to distribute label bindings within an MPLS network. The term Label Distribution Protocol can sometimes be confusing, as it's both a generic term for any protocol that exchanges label bindings and a specific reference to LDP, which is one such implementation. Defined in RFC 5036, LDP is primarily used to establish label-switched paths between label-switching routers. It is not a routing protocol. It does not carry reachability information or metrics. Instead, LDP maps forwarding equivalence classes to labels that identify LSPs. For routing table construction, LDP relies on IGPs such as OSPF or ISIS. Although originally designed to distribute label bindings for IPv4 and IPv6 prefixes, LDP is not limited to IP. It was extended in RFC 4447 to signal MPLS pseudo wires as well. The RBFS implementation of LDP supports downstream unsolicited advertisement mode and uses ordered label distribution control, meaning it only sends a label binding to its upstream neighbor if it has received a label binding from its downstream neighbor before. RBFS also uses liberal label retention mode, keeping also bindings from LSRs that are not next hops. In LDP terminology, two LSRs that exchange LDP information are known as LDP peers. Protocol information is encapsulated in LDP protocol data units, which share a common header. A key part of this header is the LDP identifier, a 6-octet field that uniquely identifies the LDP label space. The first 4 octets correspond to the LSR's router ID, and the last 2 indicate the label space. For Ethernet, a platform-wide label space is used, meaning the label is independent of the incoming interface. Media such as ATM or frame relay may use interface-specific label spaces. For platform-wide label spaces, the final 2 octets are set to 0, for example, 192.168.0.1:0. To support extensibility, LDP uses a type-length value format to encode information. An LDP PDU can carry multiple messages of different types. Each LDP message has a message type and a message ID, with the ID mainly used for referencing in notification messages. Here is a list of key message types. Hello messages are sent via UDP to discover LDP neighbors. LDP supports 2 types of neighbor discovery, the basic neighbor discovery on a directly connected interface and the extended discovery for LDP peers that are not directly connected. Initialization messages are exchanged when the session is first created and include session parameters that need to be agreed on. Notification messages communicates errors or exceptional conditions. Keep alive messages are kind of a heartbeat message sent periodically to maintain the LDP session. This ensures that the session remains active as long as both routers are operational. Address messages advertise local LSR interface IP addresses that can be used as next hops to forward IP packets. These can be withdrawn using the address withdraw message if they become invalid. Label mapping messages are used to advertise label bindings associating a FEC with a corresponding label. If this label binding is no longer needed, a label withdraw message is sent to inform the neighbor to remove the label association. Finally, a label request message is sent to request a label for a specific FEC from a neighbor. This is mainly used in downstream on-demand mode. Establishing an LDP session involves several steps. Hello messages are sent over UDP well-known port number 646 for neighbor discovery. On directly connected interfaces, they are multicast to 224.0.0.2, which represents all routers on the subnet. This is known as basic discovery. It is widely used as it automatically detects LDP-capable routers without additional configuration. For extended discovery, hello messages are unicast to explicitly configured neighbors that are not directly connected, resulting in a targeted LDP session. The hello packet includes a transport address TLV, which tells the neighbor which IP address to use for the subsequent TCP connection. Once a router has discovered a potential neighbor, the router with the higher router ID initiates a TCP transport connection for reliable communication, also on port 646. Initialization messages are exchanged to negotiate additional parameters such as label distribution mode, keep alive timers, or supported capabilities. It is important to note that LDP sessions are established between label spaces. Ethernet-based systems with platform-wide label spaces require only a single LDP session between neighbors, regardless of the number of interfaces. For peer authentication, LDP relies on TCP-level authentication mechanisms. We have already mentioned that LDP only distributes LDP binding but no routing information. Instead, it relies on the IGP to select the best path. To link the next hop address from the IGP route selection process with the corresponding label bindings, each LSR informs its peers about interface IP addresses for all its operational LDP interfaces using the LDP address messages. In case some or all of these interface addresses are no longer valid, the address withdraw message can be used to handle this. LDP periodically sends keep alive messages to maintain the LDP session. Now that a LDP session is active, LSRs begin exchanging label mapping messages. Labels are only locally significant and are automatically allocated by LDP from the router's label space. Each label mapping message contains a label TLV which encodes the 20-bit MPLS label as well as a FEC TLV. The FEC TLV is a list of one or more FEC elements with the same forwarding behavior. This presentation focuses on prefix FEC elements which represent IP prefixes. Each FEC element encodes the address family, so both IPv4 and IPv6 prefixes are supported. In the figure below, we have an example scenario with 4 LSRs in sequence. R4 is the downstream router for 2 IPv4 prefixes. It sends a label mapping message to its upstream neighbor R3 including the FEC TLV with 2 FEC elements and a label TLV. R3 stores this information in its label information base and sends a label mapping to its upstream LSR, R2. Similarly, R2 sends a label mapping message to R1. Labels are allocated independently by each LSR from its local label space and are usually not identical. R1 is the ingress LR for this LSP. When R1 receives an IP packet, it will perform an IP address lookup which results in pushing label 67 to the packet and forwarding it to R2. R2 will not perform an IP lookup, but only a lookup on the topmost label, which results in swapping label 67 with label 44 and forwarding the packet to LSR R3. R3 has received a label of 3 for this particular FEC. This label is known as the implicit null label and it has a specific semantic. It informs the LSR that the downstream LSR is an egress LR. Rather than swapping the label, R3 removes the label entirely. Loop prevention in the LDP is essential for ensuring that label-switched paths remain efficient and stable within an MPLS network. Without such mechanisms, forwarding loops may occur, causing packets to circulate indefinitely between routers. LDP employs several techniques to prevent loops during both label distribution and forwarding. On the data plane, the MPLS shim header includes a time-to-live field, similar to the one in the IP header. Typically, the IP TTL value is copied into the MPLS shim header at the ingress LR. As a labeled packet traverses each LSR, the MPLS TTL is decrement by 1. If the TTL reaches 0 before reaching the destination, the packet is discarded. This provides a basic safeguard against forwarding loops that may result from misconfigurations, routing failures, or slow convergence. LDP also implements loop prevention mechanisms at the control plane level. One method uses the optional hop count TLV in label mapping and label request messages. The hop count tracks the number of LSRs a label mapping has traversed. A maximum hop count can be configured. If this value is exceeded, the message is considered part of a loop. For example, in the figure on the right-hand side, R1 advertises a label mapping with a hop count of 1. Each subsequent LSR increments the hop count when forwarding the message. If R1 later receives the same label mapping from R4 with a hop count of 4, and the configured maximum is 4, a loop is detected. However, this method is limited. In large networks, the maximum hop count must be set high enough to accommodate the network's diameter, reducing its effectiveness as a reliable loop detection tool. Like the data plane TTL mechanism, this method prevents infinite loops but does not proactively detect them during label distribution. A more robust control plane mechanism is the path vector TLV, which functions like a path history. Each LSR adds its LSR ID to the path vector in the label mapping or label request message. If an LSR receives a label mapping that already contains its own LSR ID, it identifies a loop. Using the same example, R1 advertises a label mapping message to R2 adding its router ID to the path vector. Each transit LSR adds its own router ID to the path vector. When R1 receives the same label message from R4, it detects its own router ID in the list. Regardless of the method used, if a loop is detected, the label mapping or label request is rejected, and a notification message is sent in response. In an MPLS network, the label distribution protocol is used to distribute label bindings between routers, allowing the establishment of MPLS label-switched paths. A potential issue arises when the interior gateway protocol converges and installs routes into the forwarding information base before LDP has completed exchanging label bindings for some prefixes. In such cases, a router may begin forwarding traffic based on IP routing rather than MPLS. This can lead to traffic drops in MPLS-only network segments, suboptimal routing, or even blackholing, particularly if the core supports only MPLS forwarding. LDP-IGP synchronization addresses this problem by ensuring that a router does not advertise a route via the IGP until it has received the corresponding label binding through LDP. This mechanism ensures that MPLS forwarding paths are fully established before the IGP advertises the route, preventing premature IP-based forwarding. In the example shown on the right, all routers have established ISIS adjacencies and exchanged IP reachability information. From the IGP's perspective, the optimal path from R1 to R3 is via R2 due to lower path costs. However, due to a missing or inactive LDP session between R1 and R2, R1 cannot forward MPLS traffic to R3 via R2. LDP-IGP synchronization solves this by delaying the IGP route advertisement until R1 receives a valid label binding for R3's prefix. This ensures traffic follows a fully functional MPLS path and avoids forwarding issues. Now that we have learned how LDP works, we will configure LDP on a system running RBFS and demonstrate some monitoring commands. Let's switch to a terminal window. I've already logged into router R1. This is a virtual lab environment running an RBFS multi-service edge image, version 25.1.1. The lab setup consists of 6 routers, R1 through R6. The network topology is shown in the displayed diagram. The IGP in use is ISIS. All interface IP addresses, as well as the ISIS protocol running in the default instance, are already pre-configured. If you need more details on how to configure ISIS, please refer to the ISIS part of this video series. Configuring LDP in RBFS is straightforward. We use the CLI hierarchy set instance name protocol LDP to configure all necessary options. In our case, the instance name is default. First, we set the router ID. This step is optional. Next, we enable the interfaces hostif 0/0/1/0 and hostif 0/0/2/0, which connect R1 to LSRs R2 and R3. We also enable LDP on the loopback interface LO 0/0/0/0. Once the configuration is complete, we commit the changes. The show LDP summary command provides a brief overview of the protocol settings. We can verify the LSR ID, which matches the router ID we configured. Both the IPv4 and IPv6 statuses are set to true, indicating that the LDP configuration is currently operating in dual stack mode. We can also see the modes in which LDP is running. A list of all active LDP interfaces is shown using the show LDP interface command. This list also displays the corresponding IPv4 and IPv6 addresses that are advertised to LDP peers via the address message. The show LDP neighbor command reveals that basic neighbor discovery has detected an LDP-capable peer on each interface. The command also shows the transport address, which is part of the hello message. Additional details can be retrieved by appending the LDP ID to the command, for example, the link IP addresses, transport IP addresses, and transport preferences. Looking at the output of the show LDP session command, we notice that both LDP peers are in the non-existent state. Although hello messages have been exchanged, the setup of a TCP connection has failed. The show LDP TCP connection command indicates that TCP SYN packets have been received. Let's add the detail option to this command. The flags reveal that the remote end uses authentication, while the local side is not configured for it. LDP uses TCP authentication in a manner similar to BGP. The configuration consists of two steps. First, we create an authentication profile using the command set instance default TCP authentication profile name. In this example, we'll use LDP as the profile name. We need to define the authentication type, for example MD5, the key ID and the passkey. The configuration supports up to 2 keys to enable key rollover. In a second step, we apply the profile to an LDP session using the command set instance default protocol LDP session IPv4 192.168.0.2 authentication ID LDP. The IP address represents the transport address of the LDP peer. We repeat this step for the second peer as well. After committing the configuration, the LDP transport connection is established, and the LDP session becomes operational. Including the LDP ID in the show LDP session command provides additional session details, such as the authentication algorithm and the agreed-upon advertisement modes. To inspect the label information base, we use the show LDP binding command. The output displays the prefixes, received label bindings, and locally allocated labels. You'll also notice that both IPv4 and IPv6 prefixes are supported. As the network grows, the output may become extensive. To manage this, the show LDP binding command offers options to filter the displayed label mappings. The received option allows you to restrict the output to a specific label space, while the sent option enables filtering based on prefixes. Now that LDP sessions are established and label bindings have been received, let's examine how the label forwarding information base is constructed. To illustrate this, we'll use the loopback address of our 4 as an example prefix. The show route command reveals that this prefix has been learned via ISIS and that there are 2 equally preferred next hops. We use the show LDP address command to view the received address messages. The first next hop is associated with the label space 192.168.0.2:0. Next, we examine the received label bindings from this label space and observe that the loopback address of our 4 is advertised with a label of 20,007. Consequently, the forwarding table is built using this label, with R2 as the next hop. We can verify this by using the show LDP route command. Finally, all routes from the LFIB are installed into the routing information base, unless a route learned from another protocol has a better preference. LDP offers several additional configuration options. Using the question mark after set instance default protocol LDP CLI command provides a list of these options. For example, at the address family level, we can use the redistribute command to include additional prefixes into LDP. By default, RBFS only advertises a label binding for its loopback address. Because it uses ordered control, it also sends label mappings only for prefixes for which it has received a label binding from its downstream peer. If you want to include more prefixes in the label information base, you can redistribute them. By default, RBFS is dual stack capable, meaning it can exchange both IPv4 and IPv6 FEC bindings. To enable or disable a specific address family, you can use the status enable or disable CLI option. When LDP is enabled on an interface that supports both IPv4 and IPv6, it will begin exchanging IPv4 hellos. To send an IPv6 hello, the source address must be configured as an IPv6 address. You can also configure the connection preference to define which address family should be used for the TCP connection. For now, let's disable IPv6. With IPv6 turned off, it's also useful to disable the dual stack capability. As we've seen, the session options allow you to add an authentication profile to an LDP peer. In addition, you can apply export and import policies to filter label bindings that are sent and received. RBFS also allows you to adjust timers at the set instance default protocol LDP timer level. There are separate timers for hello messages and session messages. In both cases, it's possible to configure both the keep alive and hold timers. After deactivating IPv6, let's commit the changes and verify that the IPv6 bindings are no longer present. By inspecting the received label bindings from R2 in more detail, we can see that R2 advertises both the hop count TLV and the path vector TLV. These optional TLVs are useful for loop detection. When we examine the label messages sent by the local router to its peers, we notice that neither the hop count TLV nor the path vector TLV is included. To enable loop detection, we must configure it using the set instance default protocol LDP loop detection command. We then set the status to enable. The use of the hop count TLV is enabled by setting a maximum hop count, for example, 32. Similarly, the use of the path vector TLV is enabled by setting a maximum path vector length. For demonstration purposes, we'll also use 32 here. After committing the changes, we can verify that R1 now advertises both the hop count TLV and the path vector TLV. In the path vector, we can see that R1 appends its own router ID to the end of the list. We previously covered the concept of LDP-IGP synchronization, which helps prevent traffic blackholing. You can configure the hold timer in seconds to specify how long the IGP session should wait before declaring LDP synchronization, using the set instance default protocol LDP IGP synchronization hold timer command. The default value is 10 seconds. LDP synchronization is supported only on interfaces running ISIS or OSPF. In our topology, ISIS is in use. Let's enable LDP synchronization using the set instance default protocol SIS interface hostif 0/0/1/0 LDP synchronization enable command. We'll repeat this step for the second interface. After committing the configuration changes, let's inspect the link state database entry for the local router, R1. We observe that both neighbors, R2 and R3, are reachable with a metric of 100, indicating that ISIS and LDP are in sync. Next, we'll clear the LDP session to R2 and examine the link state database entry again. The metric to reach R2 has now increased to the maximum value because the LDP session is not yet re-established, and ISIS and LDP are currently out of sync. So far, we have only used the basic discovery mechanism to establish LDP sessions with our directly connected neighbors, R2 and R3. We will now configure a targeted LDP session to router R4 using the set instance default protocol LDP targeted neighbor command. You need to specify the address family on which the extended discovery should operate. Additionally, you must define both the IP address of the LDP peer and the source IP address. As with basic discovery, you can also enable authentication. After committing the configuration, we observe that a new neighbor has been detected. Because this is a targeted session, the peer's IP address is listed instead of an interface. We can also verify that the LDP session is operational and that we are receiving label mapping messages directly from R4. To conclude this section on LDP configuration and monitoring, I've compiled the commands demonstrated throughout the presentation into a few slides for reference. We've seen that basic LDP configuration involves enabling LDP on interfaces connected to neighboring LSRs and optionally configuring an authentication method. We also covered several advanced options, including LDP loop detection, LDP-IGP synchronization, and targeted LDP sessions using the extended discovery mechanism. We also covered some monitoring commands. The Show LDP Summary command provides a brief overview of the LDP process. The Show LDP Interface, Show LDP Neighbor, and Show LDP Session commands are useful for troubleshooting LDP session states. It's especially important to understand the difference between an LDP neighbor and an LDP session. The former is the result of the discovery process, while the latter reflects the actual LDP TCP session. The Show LDP Binding command is particularly helpful for examining the label mapping message flow and understanding how the forwarding table is constructed based on the learned address mappings. LDP is widely deployed as an MPLS signaling protocol, primarily due to its simplicity, interoperability, and scalability. However, LDP has some drawbacks that led to the development of segment routing, which we will introduce in this section. LDP played a critical role in the early development of MPLS. Its key advantage is offering a lightweight label distribution mechanism that enables the setup of label-switched paths along the IGP's shortest path. However, the fundamental question arises: why maintain two separate protocols when LDP provides no additional benefits beyond label distribution? Moreover, it's necessary to synchronize LDP with the IGP to avoid traffic blackholing. Finally, LDP lacks support for traffic engineering, as its LSPs always follow the shortest path. Segment routing was introduced to leverage the source routing paradigm. The IETF working group responsible for standardizing segment routing is called Source Packet Routing in Networking, or short SPRING. The core idea behind source routing is that an ingress node can steer a packet through an ordered list of instructions, known as segments. The segment routing architecture is defined in RFC 8402 and supports two data plane options: segment routing over MPLS and segment routing over IPv6. SRMPLS has seen wide adoption in the industry. Currently, RBFS only supports SRMPLS, so we will focus on the MPLS data plane for the remainder of this presentation. Segment routing defines three types of control plane architectures. In a distributed scenario, the segments are allocated and advertised using standard routing protocols such as ISAS, OSPF, or BGP. We'll explore the necessary protocol extensions in detail later. In a centralized scenario, an SDN controller is responsible for allocating and instantiating segments. The hybrid scenario combines elements of both distributed and centralized models. A segment represents a network instruction that is executed on a received packet. There are two types of instructions: topological instructions and service instructions. Topological instructions result in either forwarding the packet to a specific node in the network or forwarding it through a specific interface. A segment may be associated with a service instruction, used for applications such as service function chaining. In this presentation, we will focus on topological instructions. Each segment is identified by a segment identifier, or SID. Segment routing can be directly applied to the MPLS architecture with no change to the forwarding plane. A segment is encoded as an MPLS label. An ordered list of segments is encoded as a stack of labels. A segment may have a global scope, which means that any node within a segment routing domain must be able to understand it and act on it. A segment can also have a local scope. In this case, only the originating node understands its semantic. In the context of a link state routing protocol, two topological segments are defined: the IGP prefix segment and the IGP adjacency segment. For the BGP control plane, the corresponding segment types are the BGP prefix segment and the BGP peering segment. The prefix segment is a global segment associated with either an IGP or BGP prefix. The IGP prefix segment represents the shortest path to that prefix within the IGP topology. In the standard MPLS architecture, an MPLS label has local significance. It is allocated independently by each label switching router and advertised to its upstream neighbors. To construct globally unique labels without violating this principle, segment routing introduces a concept where the MPLS label is derived from two components, a base value and an index. The segment routing global block identifies a set of local labels reserved for global segments. The sRGB consists of a base value and a range. It is strongly recommended to configure identical sRGBs across all nodes in the domain. This consistency simplifies operations and troubleshooting because the same label will represent the same global segment on every node. The prefix SID is a domain-wide unique index that maps to a label within the sRGB. In the figure, SIS is used to advertise both the sRGB and the prefix SID. Each router generates a link state PDU containing its loopback address and a globally unique prefix SID. Additionally, it advertises its sRGB. While the sRGB is local to each node, it is important to the upstream neighbors, as they use it to construct the outbound label for a given segment. For example, suppose R4 advertises a prefix SID of 4, and R2 advertises an sRGB base of 5000. Then, R1, wanting to send traffic to R4, calculates the outgoing label as 5000 plus 4. R1 pushes label 5004 onto the packet and forwards it to R2. Now R2 must forward the packet onward to R4, via R3. R2 uses R3's advertised sRGB and again R4's prefix SID to calculate the new label 8004. Therefore, R2 swaps label 5004 with 8004 before forwarding the packet to R3. This example highlights why using a consistent sRGB across all nodes is operationally beneficial. It eliminates the need for intermediate label swaps and ensures uniformity across the network. The IGP adjacency segment is a local segment that represents a specific interface to an IGP neighbor. In this context, local means that only the originating router understands the semantics of the segment and how to process it. In contrast to the prefix SID, which is advertised as a domain-wide unique index, the adjacency SID is advertised directly as a label. Because the label has only local significance, other routers do not need to interpret or act upon it. Some implementations support the configuration of a segment routing local block, which is a local label range used to allocate adjacency SIDs. However, unlike the sRGB, the sRLB is not advertised to neighbors, as it is only relevant to the originating router's local operations. Prefix SIDS and adjacency SIDS can be combined in a label stack. In fact, adjacency SIDS generally require a prefix SID to function correctly. In the example below, the shortest path to R4 is through R1 and R2. However, if the source wants to steer the packet along the R1 R2 R3 R4 path instead, it can push the label stack 5002, 123, 5004. Here's how this works. The packet is first directed to R2 by using R2's prefix SID of 5002. Next, it is forwarded to R3 using the adjacency SID 123, which is specific to the link between R2 and R3. Finally, the packet is forwarded to R4 using R4's prefix SID of 5004. In RBFS, segment routing is supported for ISIS, OSPF, and BGP. We'll first explore ISIS extensions for segment routing including configuration and monitoring in RBFS. ISIS extensions for MPLS-based segment routing are defined in RFC 8667. As we discussed earlier, there are two types of segment identifiers, IGP prefix SIDs and IGP adjacency SIDs. For IGP prefix segments, SIS advertises an index value representing the SID. This is achieved using the prefix SID sub TLV, which is carried within the extended IPv4 reachability TLV, TLV135, or the IPv6 reachability TLV, TLV236, depending on the address family. The prefix SID sub TLV encodes not only the index value but also the algorithm used and additional flags. Currently, RBFS supports only the shortest path algorithm. The flags indicate whether the SID represents a node or an anycast prefix, as well as whether penultimate hop popping should be used. In addition to the prefix SID sub TLV, the segment routing global block must be encoded. This is done via the SR capability sub TLV, which is carried in the ISS router capability TLV. The SR capability sub TLV advertises the base value of the sRGB and the block size. In RBFS, you can configure a single global block for this purpose. For IGP adjacency segments, SAS introduces the adjacency SID sub TLV, which is carried within the IS reachability TLV. Unlike the prefix SID, the adjacency SID sub TLV advertises a label value instead of an index. As a result, no label block needs to be advertised. However, RBFS uses a configurable single local block for the adjacency SIDS. Let's switch back to the terminal window of R1. We're using the same lab environment as before, running on virtual RBFS instances. The topology remains unchanged, but I have removed the LDP configuration from all nodes. We can verify that two ISIS adjacencies are active, to R2 and R3. Looking at the link state database, we see 6 entries, 1 for each LSR in the network. The routing tables confirm that we've learned the loopback addresses of all 6 routers for both IPv4 and IPv6. However, there are currently no labeled unicast routes. To configure IGP prefix SIDS, we first need to define the segment routing global block using the command set instance default protocol SS segment routing sRGB. We must specify both the base value and the range. The range should be large enough to support all node SIDS in the network. The prefix SID is associated with the loopback address. We set the index using the set instance default protocol SAS interface LO 0/0/0/0 segment routing command. We assign an index of 11 for IPv4 and 21 for IPv6. After committing the configuration, we can use the show ISS segment routing global block command to display all sRGBs learned via ISS. We notice that R1 uses a base value of 12,000, while all other routers use a base value of 16,000. This is not a problem, but it's recommended to use the same settings on all routers if possible. So, let's change this. We can also view the index values learned via ISAS using the show ISAS segment routing prefix segment command. We can verify that we have learned 2 SIDs for each router, one for IPv4 and one for IPv6. Let's take a deeper look at the link state database of R1. We see that a new TLV, the segment routing capability sub TLV, is added to the database entry encoding the sRGB base and range. In addition, the prefix SID sub TLV is added to the extended IPv4 reachability and IPv6 reachability TLV. Finally, we can verify that labeled unicast routes are added to the forwarding information base as well as MPLS unicast entries. The labeled unicast are used by R1 if it acts as an ingress LR, while the MPLS unicast entries are used if it acts as a transit LSR. RBFS also supports adjacency SIDS. To configure these, we first define a segment routing local block using set instance default protocol SAS segment routing SRLB command, again setting base and range. We can then configure adjacency SIDs on ISS interfaces with set instance default protocol SS interface hostif 0/0/1/0 segment routing point-to-point. This command allows us to set the adjacency index for both IPv4 and IPv6. We'll configure both, then repeat the process for hostif 0/0/2/0. According to RFC 8667, adjacency SIDS are supported on both point-to-point and LAN interfaces. However, as of RBFS version 25.1.1, only point-to-point interfaces are supported. Once the configuration is active, we can use the show ISIS segment routing adjacency segment command to verify that labels for adjacencies are being sent and received. Checking R1's link state database again, we see that the adjacency SID sub-TLV has been added to the IS reachability TLV. Inspecting label 8412 in detail, we find that it points directly to interface hostif 0/0/1/0. Since this label is locally significant, it is popped before the packet is forwarded to R2. I've put together 2 slides that give you a quick overview of how to configure segment routing with ISS. Setting up prefix SIDS involves 2 main steps: first, defining an sRGB, then assigning an index to the loopback interface. Just a heads up, index values can't be assigned to non-loopback interfaces. You can also optionally assign an Anycast SID index to the loopback interface. If you're using adjacency SIDS, you'll need to configure a segment routing local block and assign an index to a point-to-point interface where the ISS neighbor is connected. To monitor ISS, you can run the show ISS segment routing command. This will show you the sRGB, prefix SID indexes, and adjacency SID labels. All of this info is carried in link state PDUs and stored in the link state database, which is used to build the ISS routing table. I went through the last few slides quickly, they're just for reference. Feel free to pause the video if you need more time. Let's move on to OSPF. Again, we'll provide a short overview how are the segment routing extensions implemented and will then show how to configure and monitor the operation in RBFS. OSPF extensions for MPLS-based segment routing are defined in 2 separate standards because the link state advertisements for OSPF v2 and OSPF v3 differ slightly. For OSPF v2, segment routing extensions are described in RFC 8665. Similar to ISAS, OSPF v2 must support IGP prefix SIDs and IGP adjacency SIDs. The common Type 1 through Type 5 LSAs do not provide sufficient flexibility to accommodate additional information. Therefore OSPF v2 uses the opaque LSAs to advertise segment routing information. Depending on whether the scope of the advertisement is area-wide or domain-wide, either Type 10 or Type 11 opaque LSAs are used. Opaque LSAs in OSPF are used to carry information that is not strictly required for the SPF algorithm to function. Different opaque types are defined to encode specific types of information. For IGP prefix segments, OSPF v2 advertises an index value using the new prefix SID sub-TLV, carried within the extended prefix opaque LSA. The prefix SID sub-TLV encodes not only the index value but also the algorithm used and additional flags. Currently, RBFS supports only the shortest path algorithm. The flags indicate whether the SID represents a node or an Anycast prefix, as well as whether penultimate hop popping should be used. In addition to the prefix SID sub-TLV, the segment routing global block base and range must be encoded. This is achieved via the SID label range sub-TLV, carried within the router information opaque LSA TLV. Optionally, the SR algorithm sub-TLV may also be carried in the router information opaque LSA to advertise the node's capabilities. For IGP adjacency segments, OSPF v2 introduces the adjacency SID sub-TLV, carried within the extended link opaque LSA. Unlike the prefix SID, the adjacency SID sub-TLV advertises a label value instead of an index, meaning no label block needs to be advertised. However, RBFS uses a configurable, single local block for the adjacency SIDS. OSPF v3 extensions for MPLS segment routing are defined in RFC 8666. The sub-TL versus mentioned earlier for OSPF v2 remain unchanged. The main difference is that the various opaque types in OSPF v2 have been replaced with separate LSA types in OSPF v3. For example, the router information LSA is no longer encoded within a Type 10 or Type 11 opaque LSA but has its own distinct LSA type. We are going to configure router R1 in our virtual lab environment again. The lab topology remains the same as before, and we are still using virtual RBFS instances. However, I've removed the ISAS configuration from all nodes and pre-configured a single OSPF area. We can verify that 2 OSPF neighbors are active, R2 and R3. By inspecting the link state database, we observe 6 router LSA entries, 1 for each node in the network. Additionally, R2 through R6 are already advertising opaque LSAs of opaque types 4 and 7, but R1 is not. To enable support for opaque LSAs in OSPF v2, we need to use the command set instance default protocol OSPF address family IPv4 opaque capability enable. This step is not necessary for OSPF v3. Next, segment routing must be enabled, and the segment routing global block parameters should be defined. We use the command set instance default protocol OSPF address family IPv4 or IPv6 segment routing to configure this. We'll demonstrate the configuration for IPv4 here, but the steps for IPv6 are similar. When configuring sRGB, we must specify both the base value and the range. The range should be large enough to accommodate all node SIDs in the network. To associate a prefix SID with the loopback address, we use the command set instance default protocol OSPF address family IPv4 area 0.0.0.0 interface LO 0/0/0/0 segment routing command. In this example, we assign an index of 11 for the prefix SID in IPv4. After activating the configuration, let's first check the segment routing global block using the show OSPF segment routing global block command. We observe that for IPv4, routers R2 through R6 are using different sRGB base values. Since it's recommended to use the same base value across the entire domain, let's update this configuration. Next, we verify that all routers are now using the same sRGB values. Moving forward, we examine the prefix SIDs with the show OSPF segment routing prefix segment command. We notice 6 index values, 1 corresponding to each router's loopback address. In the OSPF link state database, we observe that R1 now advertises 2 opaque LSAs. Let's take a closer look at them. Opaque type 4 represents the router information LSA and includes a new SID label range sub-TLV that carries the sRGB base value and size. Opaque type 7 is the extended prefix LSA. The new prefix SID sub-TLV is part of this LSA and includes several attributes: the algorithm, flags, and, most importantly, the SID index. Finally, to view the results of the route calculation, we can use the show OSPF route IPv4 labeled unicast command. These forwarding information base entries are relevant when the router acts as an label edge router. If the router functions as a transit label switch router, the relevant FIB entries can be viewed with the show OSPF route MPLS unicast command. Again, I have put together an overview of the configuration command as a reference. This slide summarizes the configuration steps needed to configure IGP prefix segments in OSPF. A common mistake is to forget to enable the opaque capability for OSPF v2. Other than that, the configuration is straightforward, configuring a sRGB and assigning an index to the loopback interface. In contrast to ISAS, RBFS does not support adjacency segments for OSPF as of RBFS version 25.1.1. As we've seen, we can use the show OSPF segment routing command to view the segment routing global blocks, as well as the prefix indexes sent and received across the network. We also covered the new sub-TL verses introduced into OSPF to support segment routing, which can be viewed using the show OSPF database command. These sub-TL verses are used in the router information and extended prefix opaque LSAs. In the final section of this video, we'll have a look at segment routing support in Border Gateway Protocol. In contrast to ISIS and OSPF, BGP has a different approach because it was already capable of advertising labeled information. This feature was introduced in RFC 3107, which utilizes multi-protocol extensions in BGP to advertise non-IPv4 unicast prefixes. The multi-protocol reachable NLRI inherently carries both the address family identifier and subsequent address family identifier. For IPv4 and IPv6 labeled unicast, the SOFI is set to 4, and the label stack is included as part of the routing information. Despite this, labels are still allocated independently by each router, which complicates traffic engineering when using a centralized controller. To address this challenge, BGP extensions for segment routing were introduced in RFC 8669. BGP is a highly flexible protocol, capable of supporting a wide variety of path attributes. For segment routing, the BGP prefix SID path attribute was added. This is an optional and transitive path attribute. The attribute includes two TLVs. The label index TLV, which stores the index, and the originator sRGB TLV, which encodes the segment routing global block. The originator sRGB TLV is optional. Since the BGP prefix being advertised remains a labeled unicast prefix, the label expected by the downstream neighbor is included in the NLRI itself. For example, an egress LR might advertise an index to its upstream neighbor, such as 101, while the label in the NLRI could be 3, indicating penultimate hop popping. Let's put the BGP segment routing configuration into action on router R1. This time, I have slightly modified the network topology. The network consists of 4 routers, R1 to R4, each using its own AS number. As a result, only external BGP is running, with no IGP in place. This topology is commonly used in data center environments. From the show BGP summary command, we can see that BGP is not currently running on R1. So, let's configure BGP using the set instance default protocol BGP command. We will set the BGP hostname and router ID, although these steps are optional. Additionally, we will configure the local AS number as 64501. Since we are configuring segment routing, we need to enable the IPv4 labeled unicast address family. Next, we define the sRGB base, the range value, and the prefix index. Unlike SIS or OSPF, BGP does not have interface associations, so the prefix index is configured here. We also redistribute the loopback interface into BGP. Since the loopback interface is a directly connected interface, we have pre-configured a policy named loopback, which only accepts the IP address from this interface. Next, we configure a peer group for router R2, named AS64502. We set the remote as to 64502 and activate the IPv4 labeled unicast address family. We also set the next hop to self. The BGP session to R4 is defined using its interface IPv4 address, and the peer group is associated with it. This step is repeated for router R3, which belongs to AS64503. After activating the configuration, we can verify that both BGP peers, R2 and R3, are established. The detailed output also shows that the session is using the IPv4 labeled unicast address family. We notice that we have received 4 prefixes from each neighbor. To inspect them more closely, let's use the show BGP ribbon command. The prefixes have an sRGB base and range, along with an SID index attached. Note that the label value, which is part of the prefix information, is 3 and differs from the label calculated using the sRGB base and index. The show BGP fib command displays the forwarding table constructed using these information. There is no out label for R2 and R3, as they are directly connected and, therefore, PHP is used. Using the show BGP ribout command, we can verify that we are advertising R1's loopback interface prefix, as we have redistributed it into BGP. Similar to OSPF and ISS, we can use the show route IPv4 labeled unicast and show route MPLS unicast commands to view the forwarding information base. Let's summarize what we've just covered. To configure BGPSR on an RBFS system, we need to enable the IPv4 labeled unicast address family in the BGP instance and configure the sRGB base, range, and index. Additionally, the address family must be enabled in the corresponding peer groups. The configuration for IPv6 is virtually the same. Thank you for watching this introduction to MPLS signaling protocols and their configuration in RBFS. In the next part, we'll dive into the exciting world of MPLS VPNs. Stay tuned, and thanks for your attention.